Hey, what's up? It's your old pal, Mr. Cook. We're going to work on the 2.5 extra worksheet problems. We got through the first 5 on the last video. Hopefully this one will go pretty quick because we've gone through most of the introductory stuff and we just work through it. So consider the curve given by that implicit equation. Looks like it's an ellipse that's rotated a little bit. That's what that would be. You can test it out. If you ever are interested, you can type this thing into a Desmos graphing calculator and it'll show you exactly what it looks like. I think it should just be an ellipse that has been rotated a little bit. So let's see. It says show that dy dx is equal to that, 3y minus 2x and so on. So in other words, you just want you to find the derivative. So let's do that. So we do the same rules that we went over from number 1 through 5 on the first page. Take the derivative of all the x's and all the y's. So that's an easy one. That's going to be 2x. That's an easy one. That'll be 8y. But then remember, we got to write dy dx when we take the derivative of the y part. Derivative of 7 is just 0. And then that's an x and a y multiplying. So we got to use product rule for this. So one of my functions, for the product rule is going to be 3x. The other one's going to be y. And then I do their little derivative trick. So the derivative of 3x is just going to be a regular old 3, so 3y. And then the derivative of the y part is going to be dy dx. So it's going to be 3x times dy dx. All right, that's the first step. Next step, I've got to move all the dy dx stuff on one side and all the non-dy dx stuff on the other side. So let's see here. I guess, you know what I'll do? I'm going to move this stuff over here on this side, and then I'm going to move the 2x over here. That way, I'll get all my dy dx stuff on this side. So minus 3x times dy dx. And then I'll get all the other stuff on the other side. So that'd be a 3y minus 2x. Okay, then the next step is to factor out the dy dx. So I've got a dy dx on both of these, so I'll factor it out. And then to get dy dx all by itself, I've got to divide all this stuff out, right? Because it's multiplying on there. So I'll divide it out on both sides. So 8y minus 3x. And that gives me dy dx. And it should look pretty similar to that. Yeah, look, the same thing. So there you go. That showed that it was the derivative. Show that there is a point P with the x coordinate 3 at which the line tangent to the curve is horizontal. Well, if it's horizontal, that means that the top part is going to be equal to 0. So if I set 3y minus 2x equal to 0, so that there is a point with x coordinate 3 where the tangent line is horizontal. Find the y coordinate for this. So this is where this will be equal to 0. Excuse me. So if I plug in 3 for x, 2 times 3, like that, what would the corresponding y value be? So 3 times y, right? So this is going to be 3y minus 6 equals 0. So if I subtract or add 6 to both sides, 3y is equal to 6. So that means that y would have to be equal to 2. So that would be the coordinate. When x is 3, the y value is equal to 2 for a horizontal graph. But then you want to verify it. And the way that you verify it is by showing that this is also a coordinate like in here. Okay, it should already, but you want to verify by showing that it fits in the function as well. So if we had x squared plus 4y squared equals 7 plus 3xy, these two sides should be equal to each other if I plug in 3 for x and 2 for y. So let's see if that's the case. So 3 squared plus 4 times 2y is equal to 7 plus 3 times 3 times y. We got to show that this is true. So 3 squared is 9. 2 squared is 4. 4 times 4 is 16. That gives me 25 overall on this side. And then 3 times 3 times 2, that's 18 plus 7. And yeah, sure enough, both of these are going to be equal to 25. So that means that this coordinate is on the graph. And then the other part is that this coordinate also makes the dy dx equal to 0. So both of those things are true. Therefore, it's going to be a horizontal tangent. Okay, so that's number 6, part A and part B. Next, consider the closed curve in the xy plane given by that. Looks like this one is, what would that be, like a hyperboloid or something like that? I don't know. You can graph it out and see what it looks like. It'll probably look like some really cool little shape. Consider that thing, and then find the derivative, show that it's equal to that. Okay, same rule as 6a, I guess. So it'd be 2x plus derivative of 2x is just 2. Derivative of y to the fourth is 4. Y to the third, and then since I'm taking the derivative of y, it'd be a dy dx plus 4y, so that'd be 4 times dy dx, and then equal to 0. Next, I want to get all the dy dx stuff on one side. I want to get all the non-dy dx stuff on the other side. So I'm just gonna like move all this stuff over here, because like these are the two things that have dy dx on it, right? Like these two terms. So I'll move all the 2x and the 2 to the other side. So here's what I end up with. I've got 4y to the third times dy dx plus 4 times dy dx. And that'll be equal to, let's see, if I move 2x over to the other side, it's negative 2x. If I move the 2 to the other side, it's a negative 2. Then I, do the rules that I've set in place. So like factor out the dy dx, and then divide it. So dy dx is equal to negative 2x minus 2 over all that stuff. So 4y to the third plus 4. They don't look exactly the same, so I just got to do some simplifying probably. I noticed that like I've got a negative 2 on both of these, so I'd factor out a negative 2 from both of those, and I'd get, let's see, if I got rid of the negative 2 on this thing, I'd just have an x. Then if I divided negative 2 by negative 2, I'd just get a positive 1. And then in the denominator, notice that I've got a 4 on both of these, so I'd factor out a 4, and that would leave me with y to the third for this one. And then, just a 1 on the rest of it, so plus 1. And then 2 and 4 both divisible by 2, so I can change that top part to just a negative and the bottom part to a 2. And that gets it done. That does the whole thing. Next, write an equation for a line tangent to the curve at the point negative 2, comma 1. So when you have to write an equation of a tangent line, that means that you got to write out like a linear equation. So the one that you're told to use is point slope form, which looks like this: y minus y1 equals m times parentheses x minus x1. And this is really nice because when they ask you to do that, they usually give you a coordinate, and that's going to be your x1 and y1 values. So those are freebies. X1 is negative 2, y1 is 1. And then the last thing you need to find to write out the equation is just the slope m. And the slope of the tangent line is your derivative. So since we just spent some time and found the derivative equation, all we have to do is plug in the x and the y from here, and it'll give us our derivative. So m is equal to the derivative when we plug in negative 2 and 1. So let's plug in negative 2 and 1 to that equation. So we get negative, so using this equation, we get negative x, which is negative 2, plus 1, over, then it's going to be 2 times y, which is 1 to the third, and plus 1. So we get, let's see here, so negative 2 plus 1 is negative 1, and then a negative of a negative is a positive, so positive 1. And then 1 to the third is 1, 1 plus 1 is 2, and 2 times 2 is 4. So 1/4 is our slope. So we just plug in that last little part there, and there's our line. That's an equation of a line. And I guess you can change it up a little bit. Negative of a negative is a positive, so that would make it look a little bit nicer. That's your equation of your line at that point. Find the coordinates of 2 points on the curve where the line tangent to the curve is vertical. Well, when the line is vertical, that means that the bottom part's equal to 0. It gives you an undefined slope. So what we do is we just take the derivative equations, like this thing here, and so negative x plus 1 over 2 y to the third plus 1, and we just got to find out like where the bottom part's equal to 0. So if we go to the bottom part, set it equal to 0. So 2 times y to the third plus 1 equals 0. So if we plug in, if we want to solve for y, we divide by 2. So that'd be y to the third plus 1 is equal to 0. And then subtract 1. So y to the third is equal to negative 1. And if you take the cube root of both sides, you get y is equal to negative 1. So that's like part of our coordinate or coordinates. Y is equal to negative 1. Then we got to go back to our original equation, this stuff here. We plug in for y and solve for x. So we plug in for y, we get, okay, let's see here. It's going to be x squared plus 2x plus y to the fourth plus 4y equals 5. Let's write it there so then I can use it for part D as well. So if I plug in negative 1 for y, I get x squared plus 2x plus y, which is negative 1 to the fourth, plus 4 times negative 1 equals 5. And my goal is to solve for x. So, just keep working towards that goal, x squared plus 2x. And then negative 1 to the fourth is just 1, so plus 1. Negative 4 times negative 1 is negative 4. So if I combine like terms, I get the following: x squared plus 2x minus 3 is equal to 5. Then if I subtract 5 over, I get negative 8. And then that'll be equal to 0. Now I can factor this and solve. So the numbers that multiply together be negative 8, add together be 2. That'd be negative 2 and positive 4. So that means that the two x values that I get are 2 and negative 4. Okay, so here are the coordinates that give me a vertical tangent. When my x value is 2, my y value is negative 1, so 2, negative 1. And then also when my x value is negative 4, my y value is also negative 1. So those are the two coordinates that work out for it. Is it possible for the curve to have a horizontal tangent at points that intersect at the x-axis? Or it intersects the x-axis, I'm sorry. So let's see here. Is it possible for this curve to have a horizontal tangent? So horizontal tangent means that the top part is equal to 0. So that means that negative x plus 1 equals 0. So if I divide by negative, x plus 1 is equal to 0. That means that x would have to be equal to negative 1. That's what I know so far. So is it possible to have this curve have horizontal tangents? So this is the condition that I need at points where it intersects the x-axis. So if it intersects the x-axis, that means that the y value would be equal to 0. Okay, so it'd be a coordinate that intersects with the x-axis here. It could be any point, but the main thing is that the y value has to be equal to 0. It must be equal to 0. So let's see if the y value can be equal to 0 with x being equal to negative 1. Okay, so let's go back to our original equation. So we've got negative x plus 1 over 2 times y to the third plus 1. That's our derivative equation. So let's make sure that the derivative works out. So if I plug in negative 1 for x and 0 for y, I would get negative 1 plus 1 over 2 times 0 to the third plus 1. So everything's looking okay so far, because in the top part I get a 0. That's okay. In the bottom part I get non-zero. You just get 2. So this works out. I would get a derivative of 0. So that's good. But then I also need to make sure that it actually would work in the equation. So does the coordinate negative 1, 0 actually work in the original graph, this thing? So let's see if it does. So I plug in those numbers, negative 1 for x and 0 for y. So if I plug it in, negative 1 goes in for x, so negative 1 squared, plus 2 times x, which is negative 1, plus y, which is 0 to the fourth, plus 4 times y, which is 0. And I need to make sure that's equal to 5. So negative 1 is 1. And then negative 1 times 2 is negative 2. Plus 0 equals 5. So, if I do this, is negative 1 equal to 5? The answer is no. And so what this tells you is that even though this coordinate will get you a horizontal tangent, it's not actually on the original graph, okay? It's because that coordinate does not work in this equation. So to answer the question, is it possible for this curve to have a horizontal tangent at points where it intersects the x-axis? Here's what my answer would be. I would say no. So here's why. Although, this coordinate negative 1, 0 does give a slope of 0. It is not on the graph. So, something like that would work out just fine, because not only does the horizontal not asymptote, I shouldn't use that word. Not only is the horizontal tangent there, because the derivative is equal to 0, which is something that you need. And I should write does give a slope of, oh, should I say tangent? No, does give a derivative. Yeah, let's just say a derivative. That's probably a better word to use. Because slope implies that it's like linear. That's not necessarily the case. So give a derivative of 0. It's not on the graph. Yeah, so that should be enough. Okay, so there's a second video going through the rest of the worksheet. Hope this was helpful. If it's not, just you can come by and ask questions to either your teachers, or you can come by and talk to me, Mr. Cook. I'm available in the morning or after school. Hope this was helpful, and I'll see you in the next video. Bye-bye.